then maybe we can see some ideas, some patterns that we can solve. We can see what solving is like. Okay. Of x and y. Is everybody okay? Great. Are we good now? Of x and y. And find w del x and p and del b del x and p. Okay, this is a question. This is a standard question that we solved yesterday. Okay, now so whenever I write u, v, x, y, and I give you a point, meaning the point is in this order, okay? How do I check that the points solve the system? Yeah, I plug it in. Do I need to plug it in or is it fine? Let's plug it in for v. X is 1, right? 1 plus 1, right? 1 plus 1 is 2, plus uv minus 2 is equal to 0. Y is 2, so 2 minus 3uv, so 2 minus, so 2 plus 6 is 8, minus 2v squared, so minus 2 times 4, minus 8, 2 plus 6 minus 8 is equal to 0. So it's clear that the point satisfies the system. So far so good. Should I write this down or no? That's fine, okay? Great. Now, so let's fu over fu vxy gu vxy, what is that equal to? It's x minus uq plus uv and y minus 3uv plus what? Minus 2v squared or plus 2v squared? Plus 2v squared, right? Minus 2v squared. Okay, it's clear. That g minus 1, 2, 1 is equal to 0. Okay, great. That's the first step. The second step, I need to show that u and v can be defined as explicit function of x and y near p. Near p. How do I show that? What do I need to compute? I need to compute a determinant. Right? I need to compute a Jacobian determinant. Right or no? Everybody. So what am I seeking to express in terms of the others? I'm seeking to express u and v in terms of x and y. So my Jacobian with respect of f and g with respect to u and v need be not 0 at the point p. Agree? Everybody. Now how do I compute the Jacobian at U and B at the point P? F, so what is F? I differentiate with respect to U, meaning the first variable, right? You prefer I write U or the first variable? First variable? Okay. F1 x1. And then I have G1. Now what do I have here? V, what do I have? What variable it is? F sub V, del F del V is F what? I need to differentiate F with respect to V. What variable is V in the F? 2. So I write F2. And here, V2. Okay, you can still write FV. That's fine. Okay? Even if I manipulated these, I put U, X, V, Y, you just have to pay attention. It's not always 1 and 2, but it's always U and V. Okay? Doesn't matter. So far so good? Are we good here? Yeah? Great. Let me differentiate with respect to evaluated at the point P. Then I write B. Number near B is equal, what is it? Minus 1, 2, 1. Great. Now, let's compute the derivative with respect to U. What is F1U? Everybody, with respect to U. Any question? Is it good? Is it because my xy are not here? Or something like that?
No, I'm just wondering why we're doing with respect to U, we're trying to find the function in terms of x and y.
Ah, okay. X, I mean, why are we doing this?
Like, why do we choose U and V when we're trying to
I
find
gave
it
it.
in terms of...
I gave you, do it in terms of U and V.
Okay.
This is what I did. I did this. Show that you can solve for U and V in terms of x and y.
Yeah.
But x and y are clearly a function of U and V, right?
Yeah.
You see that?
Yeah.
X is clearly a function of U and V, y is clearly a function of U and V.
Okay.
Okay? Now, I am giving you this.
Yeah.
I give you this. Okay? Is that clear? So, what is F1? Who wants to help? Yes, sir.
Negative 3u squared plus v.
Negative 3u squared plus
v.
Okay. Someone else? F2, derivative with respect to V of, yes? Derivative with respect to V is, very good. Someone else? Minus, so now we're looking G1 with respect to U, so which is minus 3V. And then now with this one, it's minus derivative with respect to V, so it's minus 3U minus 4V, right? Evaluated at the point P. Luckily here, it doesn't depend on X and Y. Magically, right? It's not, it's a coincidence. So let's see. U is what? My U is what? Minus 1, and my V is what? 2. U is minus 1, so I get minus 3 plus 2, which is minus 1, right? U is what? Minus 1. Minus 3V, V is 2, so you get minus 6. And minus 3U, so it's minus 3 times minus 1, which is 3. Minus 8 is minus 5. What is the determinant? It's 5 minus 6, right? AD, 5 minus 6. What do you get? Minus 1. Can I solve for U and V in terms of X and Y? What does the theorem tell me? Exactly. So this determinant, is it 0? No. So can I solve for U and V as function of X and Y near the point P? What assumptions did I miss? There's one more assumption that I missed, that F has continuous partial derivatives. Of course, they're all continuous. That's clear, right? So far, so good. Are we good here? The first step, the determinant is non-zero. Minus 1, 2, 1, minus 1, 2, 1. Since then U and F has continuous first partial derivatives, then U and B can be expressed as functions of x and y near P. Are we good here? Are we good? So far so good. By this function here. So far so good. Everybody, are we good? This is the next step. Yes. Any questions? Please don't hesitate to ask. Yes, sir.
It says F has continuous. What's the word after that?
F and G have continuous partial derivatives. Continuous first partial derivatives. Okay. Yes, sir.
Do we need to say that the functions are equal to 0?
Yeah, but I mean this is here, right?
Okay, but like, if I have a constant, would you have to move it to the other side to get it equal?
No, because when you differentiate a constant, you get 0. But it may not solve the system equal 0. It will solve the equal constant. But it's nicer to just repeat the concept. Yes, sir.
Does the entire function need to be continuous or just around the point?
Around the point. But here, it's continuous everywhere. So why not say, right? What do you mean the entire function? You mean the function continuous everywhere? Yeah, not necessarily around the point. The first partial derivative has to be continuous around the point, but here you get it for free, right? It's continuous everywhere. Great. Now, what do I need to find? I need to find the derivatives del u del x and del u del b del x near what point? P. What is the main idea here? What do I have to do? Maybe can I erase here? I'll erase here, and then we will find a nice pattern. Now that we established u and b are functions of x and y, right? Everybody will agree. U and b are functions of x and y. How do I obtain del x, del u del x? How do I obtain del u del x? I have two equations here equal to 0. I have two equations equal to 0. How do I obtain del u del x and del v del x? What do I do? I take the derivative, right? If I take the derivative of both f and g with respect to x, by keeping in mind that u and v are functions of x and y, then I can obtain a system. So far so good. What is the matrix, the coefficient matrix of that system? What do I expect it to be? Which one? This one. You remember this from yesterday? The coefficient matrix is this one. Let's rewrite this actually. Can I erase here? Can I erase this one? Yeah. I'll just keep the. So now we will see a pattern, and then you will help me solve for del u del y and del v del y. Okay? Now let's do del u del x and del v del x. Let's differentiate the first equation with respect to x. Okay, let's keep it in terms of f and in terms of g, not filling in the things. So I differentiate the first one with respect to x. What do I get? If u is a function of x, so I get del u del x, f1 f1 u b xy. Guys, please, who wants to help? I'm differentiating this one with respect to x, even in terms of f. So it's del u del x times f1 u v x y. Do you agree or not?
Yes.
Chain rule. The second term, what is the second term? Yes, sir. Del v del x. Okay, the third term, what is the third term? Third term? F3. What, okay. And the fourth term? 0. Very good, because when you differentiate y with respect to x, y is an independent variable now, right? So plus F3. Okay? F3 is the derivative of this f with respect to x. What is F3? Can anyone help me? What is F3? It's 1, right? Great. Now, I plug in my point P. Or let's differentiate this with respect to x again. Who wants to help differentiate the second line with respect to x? Raise your hands. One by one, guys. Who wants to differentiate the second line with respect to x by keeping in mind that u and v are functions of x and y? How do I differentiate this? Go. How do you differentiate g? The equation g. Yes? G1 uv x and y, right? Plus del v del x g2 plus g3 uv xy is equal to 0. Are we good? Thank you. Are we good here? Now what do I need to plug? I need to plug the point P. Okay? Let's plug in P. Plug in the coordinates of P to find del u del x and del v del x. Okay, what is the... Now, do I need to redo this calculation when I plug in P? This calculation, G1, G2, F2, F1, do I need to do it again when I plug in P, or I have them here? I have them here. So, what do I get? I get minus 1 del u del x, plus, how many del v del x? Minus 1 as well, right? And then what do I get here? How many del u del x? It's minus 6. And then I get minus 5 del v del x. Great. Now, I have a 3 uv xy, and then I need to have g3 uv xy. What is g3, everybody? G3 is 1. Very good, thank you. No, G3 is 0, right? With respect to x. Right? Okay, are we good here? Are we good that G3 is 0? Everybody, G3 is 0. Great, so I put the minus F3 here, so when you plug in the point P here, what do you get? Does it matter what you plug in here? No, you'll get always 1. And here you'll always get 0. So you put in this one, minus 1, and then minus 0. Yes, sir?
Does G4 equal 0 as well?
G4, no, G4, G with respect to the fourth argument, what is it? 1. G, what is that for? 0. What is the fourth argument? Y. You see a Y here? Is it clear? Great. Now, I have a system. I can solve for that, right? Everybody, is it clear? I can solve for that. Yes, sir.
I just don't understand how you got negative one up here.
Negative f3 brings the f3 to the other side. What is f3 at P, at the point P? Like 1, bring it to the other side, minus 1. Okay? Is it clear? Now you can solve. I mean, you can do it many ways, but let's do it with matrices. Minus 1, minus 1. 6 minus 5. Is equal to minus 1, 0. Right? Why minus 1? Is there a question? Oh, okay. Then you solve for value del x, del b del x. How do you solve for it? I'll give this one actually. You can do it by matrices. It's the inverse of this matrix, right? What's the inverse of this matrix? This matrix has determinant minus 1, right? So it's 1 over determinant, so it's 1 over minus 1 times AD, well, D, so A becomes D, so you flip them, minus 5 minus 1, 1, 6, times minus 1, 0. It doesn't look right. It doesn't look right because, so it's minus 5. Did I mess it up? So let's see. Minus 1, minus 5. What's the determinant? It's minus 5 plus 6. No, the determinant is 1 here, right? It's 5 minus 6, so it's minus 1. What happened? Minus 5 minus 1. So it's 5. I made a mistake somewhere. 5. Yeah, so 1 over that 8. The determinant, what is the determinant? It's 5 minus 6. So it's minus 1, no? And then you flip these two, and you reverse the sign of these two, and you multiply by minus 1, 0. So it's 1 over that 8. 5 minus 6, the determinant is minus 1, do you agree? Let's see if I messed up. I messed up somewhere, I'm sure. So it's 5 minus 6. Where did I mess up? Should it be deep? Minus 1, minus 6, I have that. No, it looks good, right? The solution in the book says it's good. Value del x is minus 5. That's right. Value del x is minus 5. So what is that? Value del x is 5 minus 5. And then 6 minus 1 is minus 6. Yes, sir?
Why don't you have it in total?
Well, I'm differentiating with respect to x, right? Y is an independent variable. U and V are functions of x and y. Okay? Everybody, this is good? Okay, now if I ask you to find del u, del y, and del v, del y, how do you do that? Let's try to do it quickly. Look at the pattern here. How do I write down a system for del u, del y, and and del v del y. Always, this is, you know, a good way to remember this, that this is del f del u times del u del x. Okay? This is del f del v times del v del x. Okay? This is one way to remember it. And you differentiate f with respect to x by assuming all the variables are independent, right? When you take f3, you're assuming all the variables are independent. Okay? Great. So let's try to set up a system for del u del y and del v del y. Minus 1. Yeah. Minus 6. Minus 5. Del u del y. Del v del y. What is it equal to? It's minus f4 at the point minus g4 at the point, right? What is f4? Zero, right? And what is g4? G4 is what? Is 1. So this is equal to 0 minus 1, and then you cancel. Okay? Are we good here? Great. Okay, so it's a pattern that you can use. If you don't use it to rewrite everything, it's fine. I prefer that you rewrite everything every time. Great. Let's do this now. Let's finish. Done with the implicit function theorem. Now we're going to talk about directional derivatives. Okay? So this is an easy part of the course. Okay, now we're going to go back to easy stuff, basic calculations. Can I rate this? Yeah? So I'll post a quiz maybe today or tomorrow, and everything that is due next week will be pushed to Friday. Okay, so that you have time to study for your midterm. I don't know if I have things due on Wednesday, right? Or Tuesday?
The last thing is this Friday.
The last thing is this Friday. Okay. This Friday, I mean tomorrow.
Yeah.
Okay, so everything that I will assign this week, today, will be due next Friday. Okay, so nothing will be due before the midterm. And I'll give you some time between the midterm and things like that. Okay, and you know, to do the homework. Anyway, so now let's talk about directional derivatives. Okay, we have seen the derivative. If f is differentiable at x0 y0, how did you define the partial derivative? We defined it with respect to x as the limit as h approaches 0 of f of x0 plus h y0 minus f of x0 y0 over what? Over h, right? This is how we define the rate of change with respect to x. And if you remember, we saw that, you know, we took a paper, and then we saw that, you know, if you slice the curve with x equal a or y equal b, right? You obtain a curve, and then you derive the tangent line, right? Remember this? This is how we did this. This is how we derive the tangent line. This is the rate of change in the x direction, and in the y direction. y0 plus h over h. Now let me write this another way. I will write this as f of x0 y0 plus h times 1 0. This vector we'll call I over h limit h as goes to 0 plus h times 0, 1, which I'll call j, over h. We agree? I just rewrote x0 plus h y0 as x0 plus h times 1, 0, right? Do we agree with this? Everybody, do we agree with this? Yeah? This is easy, right? So really, I'm measuring the rate of change when I compute fx in the direction of what vector? And true, in change of x, true, but in what vector really? What is the vector? It's the vector I, right? And then when you're doing f sub y, you're measuring the rate of change with respect to what? J. Okay? Now, I and j are unit vectors. What if you want to measure the change of direction, or the rate of change of f in the direction of a unit vector u? So pick u be a unit vector. What is a unit vector, everybody? Unit vector, what does it mean? It means that a squared plus b squared is equal to 1. Let's see how to do that. In direction okay. So let's do something. Vectors, do you prefer that I put like arrows on them or not? Do you prefer arrows on vectors? Okay. Okay, so I'll try to put arrows. I used to be good with the arrows, now I'm worse, so I forget them every time. But anyways, now what is the idea? You remember how did we find the rate of change of f in the direction of x? How did we try to derive it? We took a plane, x equals a, right? You remember this? We took a section, and then I have a surface z equal fxy, and it cut my surface in a curve, right? You remember this? Right, so I cut this here, and I have a curve here, right? You see that? Cut it like that, just stop like that. So if you have meat, for example, and you cut it along a curve, right? If you cut something, a vegetable or something, you cut it along a curve, right? You see that? Well, I mean, wow. Not exactly, because it's 3D. It's like it has something inside. But anyways, but yeah. Anyway, when you cut along a surface, and the boundary of that surface is a curve, right? You see that? Anyways, now how do I put my vector u? So fix x0, y0, z0 on the surface. Z is equal fxy, xp, a point P, where z0 and this is my vector, my unit vector u. Now my idea, so this is P, the idea that we may want to use is the same idea. I take this plane that goes through P that is vertical. So before we took the plane that goes through P that is parallel to the x-axis. We took it this way. Now, P is here. I'll take a plane that passes through P, but is not necessarily x equal a or y equal b. So this is the x equal a plane, or x equal x0, right? And then I can take another plane through the direction of this vector here, right? You guys see that? Yeah? Now, how do I describe this plane? What are two vectors in this plane? From linear algebra, what do you know? U is a vector in this plane. U is a vector that is parallel to this plane. And what's another vector that is parallel to this plane? If you pick a plane like this is X, this is Y, and this is Z. If I pick a plane like that, this plane, what is a parallel vector to it? Sure, every vector here, and what as well? U is a parallel vector, not every vector. U is a parallel vector. And what's another parallel vector? Z, right? K, right? Take the plane. And of course, are U and K collinear? Are they parallel? Or U lives in the two-dimensional plane in X, Y, right? And K lives in 0, 0, 1, so they're not parallel. You see that? Okay. Consider the plane passing through P0. P, I call it P or P0 through P, and spanned by AB0, right? This is U, but in 3D, and 0, 0, 1. Okay? I mean, this you don't have to know, this is just a motivation. Now, let X, Y, Z be a point on the curve of intersection. Consider the plane, what are we going to call the plane? Consider the plane, what's a good name for a plane? P is a good name, but you used it already. Let's put it Q, okay? And planar geometry. Consider the plane that is a section C of Q, and Z is equal to Fx1. Okay. Now, you have a point then. Yes, can I help?
Passing through P and spanned by AB0.
AB0 and 0, 0, 1. Are they equal to 3?
No, it's fine.
Okay, it's fine. AB0 and 0, 0, 1. You see that? Two vectors and a point give you a plane. Two non-parallel vectors and a point give you a plane. Right? You see that? Awesome. Great. Now, I am on this plane, and I have a curve of intersection. Take a point that belongs on the curve of intersection of the surface and the plane. What can you then say? You can say that X, Y, Z, or X minus X0, Y minus Y0, Z minus Z0 is a linear combination of what? Of AB00 and 0, 0, 1. You agree? The difference of these two vectors, so you take a point X, Y, Z, so you have your surface here. This is the curve of intersection of the plane and the surface. You have a point P here, and you have a point Q here. Now this vector lies in the plane. If a vector lies in the plane spanned by AB00 and 001, then you can write it as a linear combination of these two, right? You see that? Linear algebra? So we can say that X minus X0, Y minus Y0, Z minus Z0 is, let's say, H AB0 plus, I don't know, plus T001. Okay? what is x in terms of x0? X is just x0 plus HA, y is y0 plus HB, and z is equal to z0 plus b, and what I have. Yeah. Check. I don't know if the book does it the same way, but if it doesn't, I think everybody does it the same way. I'll say that. Okay, so far so good. So far so good. Just a second. Yeah. Okay. Well, now, what is Z really? Z is Z0, sorry, is fx0, y0, right? You agree? By definition, we wrote this here. Now, what do I have to do? What is the rate of change of f of PQ, say, of between x, y, z, and d? So, the rate of change, the difference of f, so it's f x, y, minus f of x0, y0, which is, what is that? This is just f of x0 over what? Over what? Over h, right? You see that? We see that? This is the rate of change. We see that or no? We see that delta f over. Okay. So what do we call this? Fx minus over h. Yeah. So this is just f x0 plus ha y0 plus hb minus over h. And I take h to 0 and I get a derivative. You see that? You get a derivative. Yes?
How did you find that D0 is f of x0 or 0?
Oh, because by definition, right? This x0, y0, z0 is on the surface.
Oh.
Okay? Are we good here? This is the derivation of it. Anyways, we'll have a very nice notation. I mean, what's the distance between xy and x0, y0? If that may help. What's the distance between x and y and x0, y0? What is it? Yeah, it's it. H, right. You see that? What is the distance? It's the square root of h squared times a squared plus h squared times b squared, which is h. These 2 points have distance h. x0 minus y, x minus x0, y minus y0. These two have distance h. You see that? Okay? Yes, sir.
Why isn't Z equals to Z naught plus HT?
2.
HT, because it's T.
What is T? I don't understand.
Never mind.
Okay? Anyways, so, the directional derivative of f, which is a function of xy, in the direction of a unit vector. And here we didn't use this, right? Of a unit vector, u, AB, is denoted by du of f at x0, well, what did I say? Yeah, in the direction at the point at x0, y0 is denoted by what? Du f at x0, y0, which is the limit as h approaches 0 of x0 plus ha, y0 plus hb, minus fx0, y0 divided by h. Great, I mean this motivation is cool, but unfortunately we will be doing something else. Now, what is this derivative? Can you simplify this? Can you simplify this? How do you think you can simplify this? What is fixed here? X0, Y0 are fixed. A and B are fixed. Great. Let me write it this way. So if you plug in h equals 0 here, what do you get? Plug in h equals 0 here, what do you get? fx0, y0. This is gh minus g0, where gh is what? Right? You agree? gh minus g0 over h. You agree or not? What is gh minus g0 over h? The limit as h goes to 0 of that. If I put this here, x minus a over x minus a as x approaches a. This is the derivative of b at 0. You agree or not? Calculus 1? No. Limit of fx minus fa over x minus a as x approaches a is 0. Or you can take it as limit as h equals 0 of g0 plus h minus g0 over h. That's fine. What is g prime of h now? Who can help me differentiate g? How do you differentiate g? What do we use? Chain rule. So who can help me? Help. How do you differentiate g? So I have one variable function, right? G is a one variable function. and the two arguments in f depend only on h. How do I differentiate this? How do I differentiate this? Do you all know how to differentiate this? Yeah? With respect to h. So, what's the derivative of the first argument with respect to h? A. Times what should I put? F1, or I'll write it fx. Very good. Or with respect to the first argument, applied here, plus, what is that? B, F. Thank you very much. Thank you very much. Right? Are we good here? What is g prime of 0? What is g prime of 0? Plug in 0, what do you get? You get A. Plus B, plus B, plus B, plus B, what? Fy. I'll write it this way. AB dot okay. Is that clear? Are we following? Great. So really the directional derivative of f in the direction of a unit vector AB is what? It's just the derivatives fx fy at the point dot the dot product with AB. Are we good here? Are we good? So hence du x x0 y0 is what? Is fx x0 y0 fy x0 y0 dot a. This vector we call it the gradient. Fx fy called the gradient. So the gradient of f at xy, what is that? This is just fx xy fy xy. Okay, are we good here? Are we good, everybody? What do we call this vector when you take the partial derivatives and you put them one after the other? What do you call it? The what? The gradient. Am I writing a bit fast or okay, because so far so good? So what is the directional derivative in the direction of a unit vector? It's just the gradient at that point dot AB. So far so good? Yeah? Okay, let's do an example. Of course you can generalize this to 3 dimensions and higher dimensions as well. But let's do an example. Let's pick one from the book. Should I pick one from the book or give my own? Let me pick one from the book. I think it's better. Easy or hard? Hard. Okay, so easy has more. Has more. Okay. Find the gradient of that. I mean, it's just a derivative. And directional derivative. Of f. Well, I'll give my own time, f11 in the direction of 3, 5, 4. Okay, is U a unit vector or not? 3, 5, 4, 5, is it a unit vector or no? It is, right? It is, no? Yeah. Great, let me do this now. wants to give me a nice function? Let's say x over y is nice. X over y is good. Okay, great. Now, what is the gradient of f at xy? The derivative with respect to x, what is the derivative with respect to x here? What is fx xy? What is fy? What is fx xy, everyone? 1 over? 1 over y, no? Yeah. And what is fy xy? It's minus x over y squared, no? Great. Now find the direction of the gradient of f in the direction of u. What is that? Add the point 1, 1. Not u. What is that? This is just 1 minus 1 plus 3 over 5 or 5, which is minus 1 over 5. We do one more just to have fun a bit. Is it clear or not? That's clear, no? You just gradient dot u. One more? We do one more, let's do one more. Up. Okay, let's do a harder one. Find du of x at x0, y0 if fxy is equal to x squared ln y and u is minus 5 over 13 and 12 over 13. Is u a unit vector? 5 squared plus 12 squared, what is that equal to? 169. 13 squared is 169, right? So u is indeed a unit vector. How do I find the directional derivatives? First, let's say 2, 1. Does the book have 2, 1? Doesn't matter. Well, the book has 3, 1. Doesn't matter. Okay. How do I find? First, I find the gradient. What is the gradient? I differentiate with respect to x. I get 2x ln y. And then I differentiate with respect to y, I get x squared over y. Now du of f at 3, 1, this is just the gradient of f at 3, 1 dot u. What is the gradient of f at 3, 1? What is ln 1? 0. So it's 0, 3, 1, 9 over 1, 9, dot minus 5 over 13, 12 over 13. What is that equal to? 9 times 12 over 13, 108. Okay. Is that good? Is that clear? Is that clear? How you do it, or one more? Should we do one more? Should we do one more? That's fine. Is that fine? How you find the gradient? You take derivatives, the partial derivatives, you plug in the point, and you dot product with u. That's how you get your directional derivative. U should be a unit vector. Anyways, this is easy stuff. Easy calculations, I assume. We will move on to slightly harder calculations. And I'll give you the property of the gradient. Okay? I'll prove one of them. And then you'll have to prove the other one as exercises. So let's usually be differential with, let's say, 2 variables. In 2 variables. So say x and y. Okay? Then, what do I have here? Let A and B be numbers. Then, the gradient of AU plus BB is equal to A gradient of U plus B gradient of B the gradient of UV is V gradient of U plus U gradient of V, and the gradient of U over V is what is that? It's U prime V, so it's V gradient of U minus minus U gradient of V over V squared. Okay, this is a chain rule, a derivatives rule for the gradient. Let's prove one of them. Which one do you want to prove? Which one do you want to prove? This one is easy. This one is like a product rule, right? You see that? This one's like a product rule. Let's prove the second one. So you have 1, 2, 3. The first one is an addition rule. The second one is a product rule. So let's prove the second one. What is the gradient of U? The gradient of U is Ux, Uy. You agree? That's the gradient of U. Yes or no? Yeah? What's the gradient of V? Vx, dy. Huh? Do you agree or not? That's the definition of the gradient. What's the gradient of UV? Oh, let's write this for it. The gradient of UV, sorry, I'm speeding up a bit. This should not be very tough. What's the gradient of UV? This is UV x, UV y. We agree or not? You take the gradient of a function, derivative with respect to the first argument, derivative with respect to the second argument. How do you differentiate this one with respect to x? Uxv plus vxu, right? How do you differentiate the second one with respect to y? Uyv plus dyu. We agree or not? So far so good. Okay, now what do I do here? Notice something. I can write this as Uxv yeah, how do I write that? How do you think you can write that? Uxv Uyv plus vxu dyu, right? Now I can factor v out because v is a scalar function. I can factor it out. So it's v uxuy plus u dx dy. What is that? This is just v, the gradient of u, plus u, the gradient. Okay? So we prove that. Now we'll just give an interpretation of the gradient. Should we do like something like second, should we do another exercise like that, a bit fast, but meaningful exercise, or that's fine? Yes.
I just have a question. Do you
Yes, sir.
How to prove this?
Pardon me? Yes, you need to prove this. Yes. 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 Yeah, you need. Pardon me? Yeah. It's just product rule, right? This is product rule. Product rule on each of the sides. This side product rule, and then you split it up. This is quotient rule, but on each of the sides. Well, no, this one's a bit, yeah, sure.
You need to prove all of them or just some?
No, all of them. You know, the third one is up as an exercise. I mean, I can do it, but it's a. You want me to do it? You want to do the third one? Sure, let's do the third one. What is the gradient? What is the gradient of u over v? What's the first term of the gradient? This is uvx, uvy, right? Yeah? What is UVX? This is just VUX minus UVX over V squared. Agree or not? What is UVY? This is VUY minus UVY over V squared. Let me do the, now what do? I can take a V squared out, right? Well, let's keep the V squared, so that's fine. Let's take a V squared out. And then what do you get? How can you take your V? So take a V here. VUXUY, right? Minus UVXVY. This is just 1 over V squared, or this is just V radius of U minus U radius of V over V squared. Okay? So good? The first one is easy to prove, right? The first one is very easy to prove. Okay? The first one you're just adding stuff. Anyways, great. Now let's give an interpretation of the gradient. That's good. That's good. Yeah, sure. That's fine. Do you want to do another exercise on directional derivatives or not? Do you want to do one like that? We can do one quickly. Do you guys want to do something on directional derivatives? An exercise? A proof exercise. We can do a proof exercise. Let's do that. Okay. Let f be differentiable and suppose be twice, so 2 times, and suppose fxy and fyx are continuous. So if fxy and fyx are continuous, what can I say about them? They are equal by, what's the theorem called? Clairaut's theorem, right? Great. Show that and let you, yeah, you did that. Show that du of du fxy is equal to, let's see, I never memorized this. A squared, B squared, 2. Oh, yeah, that's nice. Or you know, let's add a point, say x0, y0. What? xy, x0, y0. This is very nice. I mean, the idea is not that bad. Let's first start by writing du, or you know, what do you prefer? We prefer put xy, we can put xy. Okay. How do we do this? I think this was on a final like 2-3 years ago, so it's a good question. It's a good question. How do you do this? Yes, sir. Yeah.
How did you go from the vector you had
Yeah.
before to
Here?
Not 1 over V squared?
Here?
No, yeah.
This one? How did I go from the vector before? So what did I have before? I hope I have it. It's VUX minus what? UVX, right? Over V squared. And what did I have? VUY, right?
Yeah.
Okay. So subtract these two, what do you get? Do this operation. VUX minus UVX is the first component. It's here. Look at the second component. It's VUY minus UVY. It's here. Okay? Is that clear?
But like, they're common separated, how are you allowed to?
Add these two up. Can you add them?
Yeah.
If you add them up, what do you get?
Not-
Fine. That's good.
But they're like common separated.
What do you mean from like here, between here and here?
It's kind of like they're two different things, how you combine them.
Are they? So this is. Right?
Yeah.
And you can still write 2, 2. So this is 1 plus 1. 1 plus 1. Okay? You can separate it. Right? Yes, you can. What's x plus y? A plus b. This is just x. So x here, y here, right? Add them, what do you get? Then you get a here, b plus. Yeah. I mean, there are other combinations. You can say xb, right? Great. I mean, I'll leave it as an exercise. Try to do it as an exercise, actually. Okay? It's a nice exercise. Just test that you know this stuff. It should be 2-3 lines. I mean, if you want to do it, I can do it, but should I do it? Let's do it, but let's make sure I have a good definition. Okay, so let's do this. What is du fxy? This is just gradient fxy dot u. We agree or not? Yes, by definition. This is just a fxy plus b fy x1. Great. Now let me take, I want to take directional derivative of this function with respect to u. So I need to take the gradient of this function. Right? And dot product it with u. Right? So I'll call this gxy. So du fxy is equal to what? To what? It's the gradient of g xy dot u. What's the gradient of g? First component, what is that? It's a fxx plus b fyx. Agreed? Differentiate g with respect to x, you get fxx plus b fyx xy. And what's the second component? Differentiate with respect to y, you get a fxy or plus b fyy, right? Right, you can see dot u. Okay, sorry if you cannot see. And then what do I get here? Let me write this. I mean, I can't read this. This is a nice proof. I mean, I'm doing it fast. You can try it at home. It's a good, what did we say? It's a fxy plus b fyxy times what do I have here? What do I have? A fxy xy plus b fyy xy dot u, which is ab. U is ab, sorry. Okay, how do I do that? Just take the dot products, right? So it's a squared fxx, right? Plus ab fyx xy plus ab get this, a squared. Now, if you see something like that on the final, please don't say you didn't see it, okay? X. Okay, great. Okay, so if you see something like that, just don't say you didn't see it or you saw it and you know how to do it. Great, awesome. Enough? Let's interpret the gradient. That's an interesting question, though. It's a very good one. And it's very quick, no? It's quick if you know the formulas. What time is it? Do we have an hour left?
Yeah.
Okay, good. Yes, sir.
So after 280, there are also known as y.
Exactly. Why is that? Fyx is fxy are equal.
That's the reason for equal.
Are equal, yeah. By Clairaut's theorem, right? Because fyx and fxy are continuous, so they're equal. Yes.
I have a question about the Jacobian.
Okay, what is it?
Not related.
Sure.
So, for the Jacobian, it only works if you have
Guys, hey.
two functions, two variables as functions of other variables, only two.
No, I think yesterday we.
Yeah, you did like y up to y.
Yeah.
But how would you do it in a 2 by 2? Like,
What do you mean? A 3 by 3? You have a 3 by 3 determinant then.
oh, okay.
Yeah.
So,
Okay.
and also, before you said that you had something with x and u and v, you wanted to show that u and v were functions of x and y.
Yeah.
But it could also be shown that x and y are functions of u and v.
Yeah, but
Doesn't matter.
depends. I mean, in that context, in that problem it was clear because I already had x is u cubed plus something, right? You can show, like you can pick any variables, right? Yesterday we saw like any variables you can pick as long as the conditions are met.
So you just consider whatever you want as long as the conditions are met.
Exactly. I mean, usually you need to have the number of equations as the number of variables you need to express in terms of the other.
So you can ignore the fact that x is also a function of u and v and just treat x as an independent variable.
Exactly. Yeah. This is the implicit function. This is the implicit function here. Okay. Great. Awesome. Great. Let's interpret the gradient and then move on to serious stuff. This is easy stuff. Okay. This is just calculations, very routine calculation. I mean, I did a proof just to make it to change the vibe of it, of like plugging in numbers. Something like that is fair game. And things like this, the gradient business is also fair game. So you can expect some of these to show up. You can expect, I'm not saying they will, but I'm saying you can expect. Okay, that's a proof question, long answer. Let's say, I don't know, 10 marks, 8 marks, free. And then, okay, where's my notebook? Okay, I'll interpret now the gradient. So because Wednesday we're starting a new thing. Wednesday we're starting integration. So Monday there's no school. Oh, by the way, Monday there's no university, right? Monday is Patriots Day. Yeah, Monday is Patriots Day, so there is no university. Monday is off, no? Monday is the Journée des Patriotes, so it's off. Tuesday is the midterm. So I posted office hours. So tomorrow I'll have extra office hours online from 4 to 6. I'll post the Zoom link. Someone told me to not post the Zoom link, so I'll post it. And guys, hey. So yeah, so I'll post the Zoom link, and then and then I added an hour of office hours after the lectures. Tuesday and Wednesday, right? Is that it? Monday because Monday we usually have a exercise session. Okay, now are we interested in rescheduling this exercise session or not? That we are missing on Monday or not? Are we interested in rescheduling it? Okay, so I'll try to reschedule it. Perhaps next week, okay? I'll not do it tomorrow. I'll do it after the midterm maybe. And Monday you don't have tutorials, do you? So if I put the review session, the exercise session on let's say Tuesday or Wednesday, is that fine? Will that be a long day for you? Tutorials and lectures? Is that fine? Is that fine? Is that fine for everybody? So I'll try to reschedule it on Tuesday and Wednesday. We'll do a lot of problems. We will do like a lot of problems, so I have many problems ready. Okay? So now we'll just interpret the gradient. Okay, notice that what is du f at x0, y0? This is just the gradient dot u. We agree or not? This is what we have shown. Yes? Now, what is gradient dot u? What is that? Let's go back to linear algebra, or to, to planar geometry. What is the inner product, or the scalar product of two vectors? It's the norm of gradient times the norm of u times what? Cosine of the angle in between the two vectors, right? Remember this? Where theta angle between. Now, this is the norm of and u. This is the norm of the gradient. What is the norm of u? U is a unit vector, so what is the norm of u? 1. This is cos theta. Now, when is this maximized? When is cos theta maximized? When theta is equal to 0, what is the value of cosine theta? If theta is equal to 0, what is the value of cosine theta? 1. So what is the value of the directional derivative? So if it's different than 0, 0, when is the gradient maximized? This quantity, duf x0, y0 is maximized when u let's read this. Right? We did it before. When is the dot product of a vector by unit vector maximized? When the unit vector is the vector over the modulus of the vector, right? Did we see this? Yeah, we saw this or no? Algebra 1, linear algebra. Did we see this before or no? Yes or no? No, there's a yes or no answer. Did we see this before? Yeah? Yeah. We saw this, right? Okay, so this is maximized if theta is equal to 0. You agree? Right? So if theta is equal to 0, you can say that u is k times the gradient, where k is a positive number. You agree? You have seen that? So u will be k times the gradient, where k is positive. How do you find k? What is the norm of u? The norm of u is 1. So the norm of u will be equal to the absolute value of k, which is k because k is positive, times the gradient, times the norm of the gradient. is 1. So k is 1 over the norm of the gradient. Yeah? Yeah, okay, we saw this. We saw this before. Yeah, okay. Yeah, linear algebra is very, very, very important. What's up? I erased it? Oh, I should have kept it?
Yeah.
Oh, okay. So this is, if this dot product is maximized, if and only if u is k times the gradient, where k is positive, right? Now since the norm of u is 1, then what is the norm of u? The norm of u is absolute value of k times the gradient. Right? Now k is positive, so what is the absolute value of k? Is equal to k. So k is that. Now what is the norm of u? The norm of u is equal to what? To 1. So solve for k, what do you get? K is 1 over the norm of the gradient. So u is the gradient over its norm. Okay, we agree? We saw that? Great, awesome. Oh my god, I'm sitting because I want to write there. Man, I guess with age people. Anyway, with age I start losing it. I still feel it's too early, but sorry about that. I mean, there's the recording. You can rewatch it. Okay. Estimate the time. What is the time now?
12:32.
12:32. What time did you start? 11:05. So 1:25. You can rewatch the recording. Okay. But was it clear? Okay. Okay. Yeah, because I wanted to write something. We say that at x0, y0, f has the maximal rate of change in the direction of at this rate and this rate of change equals. So if I want to plug in u here, what do I get? I get the gradient times the gradient divided by the norm of the gradient. So you get the norm squared, the norm of the gradient squared divided by the norm of the gradient, right? A dot A is norm of A squared. Yeah? So, equals. I'll write it all so that I don't erase it. What, yes. Okay? Great. Enough with gradient business. We'll continue with more interesting stuff. Okay? Is it clear? So if I tell you what's the maximum rate of change, in what direction you get the maximum rate of change of the function f(x, y) at a point, it's in the direction of the gradient. Okay? That's what it says. Yes, sir?
You mind explaining like the first line of notice that and the second line? How will they equal each other? If you have u equal to gradient of f.
Where? So this?
On the right, with close data.
Yes.
And under you have another thing. How is that equal?
U is the unit vector. Directional derivative is with the unit vector, right? What's the norm of unit vector? 1. replace normal q by 1. You're wondering where the cosine theta is coming from?
No, no, no.
That's fine.
You're saying more with a,
Norm, yeah. Length. Length. Did you see the word norm before? Norm, length, yeah, okay? Well, I don't know. The same notation, okay? Square root of a squared plus b squared, or if you're in space, square root of a squared plus b squared plus c squared. Great, awesome. That is fast, but we'll move on to interesting stuff, I guess. Great. So what time is the tutorial? It's 10 to 11, 10:05 to 10:55.
Correct.
And the class is at 11:05.
Correct.
Okay, so Monday you have a midterm from 10. Tuesday, you have a midterm from 10:05 to 10:55. Okay, so Tuesday, do you mind if we shift the class 10 minutes? So like we start at 11:15 and we finish at 11:35? Yes? In the same tutorial room. Engineering 304?
Yeah.
Yeah.
Oh, it's my turn.
Is that engineering 304?
Yeah.
Yeah, this is the room that they gave. So like we asked, hey, can you switch? Engineering 304. Yeah, so it will be there in the same room. And is it a bad room?
No.
Is it a good? It's a better room.
Yeah, it's good.
Is it a good room? Is it spacious?
Yeah.
Can you sit like? I mean, it doesn't matter. But can you sit like one?
Probably, yeah.
Like okay. And tutorial attendance, how much is it people are attending?
Half the room.
Okay. Well, I hope they'll have a chance on Tuesday. Anyway, so maximum. Yeah, but please take it seriously. It's gonna be straightforward. The midterm is gonna be straightforward. If you found the quiz straightforward, the midterm will be straightforward. Okay, so please study and don't mess it up. The quiz was the quiz easy? Medium? Hard? Was it hard? So review your notes, review your quiz, and the midterm should be like the quiz. I promise you, okay? It's gonna be like the quiz. I'm telling you, it's gonna be like the quiz. Okay? Not exactly the same, but it's gonna be the same idea, the same thing. Okay, mark down anyone's back. Okay, great. So in Calc 1, okay everybody, in Calc 1, yes sir. Oh man, I should really work on my handwriting. And minimum. Okay, so in Calc 1, a lot of the study of derivatives was, a lot of the chapter of derivatives, a big part of it at least was, or consisted of finding local max, local min, absolute max, absolute min, and things like that, right? You remember this? We're going to do the same now, but in 2 dimensions. Things that will change a bit. So what did we have for our local, to find if I have a differentiable function? What test did you do at the critical point? The second derivative test, right? Now we're going to also do a second derivative test in that case. Okay, but it's going to be way different. It's not going to be the same, but it's going to be a bit different. But that's what we're going to do. Okay? So, let's write some stuff. And this is stuff that is, we take f from r squared to r. Okay, now it could be defined on a smaller set. Guys, it could be defined on a smaller set. Okay? Not necessarily r squared, but Okay, now, if for all xy, fxy is less or equal to fab, what do you call fab? In Calc 1, what did you call? If fx is less or equal than f of c for all x, what did you call f of c? Max? It had a word before. I heard it, yeah? I heard the word. It starts with A. Absolute maximum, right? The same thing here. Just definition. If fxy for all xy, we say that fab is an absolute maximum. Obviously, absolute for and well. To say that f has an absolute max at AB, the absolute maximum, the absolute maximum, or the value of this means. Okay, so local and absolute minimum can be defined in a similar. Okay, so you just have to edit. Local min means that xy is lesser is bigger or equal than fab for all xy equal AB, and absolute min fxy is bigger or equal than fab for all xy. Great, awesome. Now, in calculus 1, you said f is differentiable at a point, and f has a local max or min. What can you say about the derivative of f at that point? It's called Fermat's theorem, I think. You saw this? Say f has a local maximum at a point, and f is differentiable at that point. What can you say about the value at that point? The derivative at that point is 0, right? Everybody remember this or no? Same thing here. That's nice. Suppose theorem. Suppose f has a local max or min at AB, and fx AB fy AB exists, then fx AB is equal to 0, and fy AB is equal to 0, and the gradient of f at AB is equal to 0. Do you want me to prove? You're not in charge of. You're not responsible for the proof of this theorem. Do you want me to prove it or not? No? Some don't want to hear the word even. You're not responsible for proving this. Do you want me to prove it or not? No? You can believe me on this fact? You trust me that if f has a local max or local min at a point where it's differentiable, then each derivative must be 0. Okay? Do you trust me on this fact or am I to prove it?
Yes.
Prove it? We trust me?
Yeah.
Trust me? Okay. Great. Okay. We say that AB. So a lot of these statements you won't be in charge of proving. Any of those that are coming in this lecture and the lecture after. Do you want me to omit the proof? I omit the proof.
Only we need to know.
No, of course, if you need to know it, I'll do it. Okay? If you need to know it, I will do it, definitely.
Do you think you'll help us understand it more?
Pardon me?
Do you think you'll help us understand it more? Do you think proving it will help us understand the concept more? Like,
I don't know. Maybe, maybe not. Depends. Depends on each and everybody. Yeah, depends on each and everybody. Okay, we said it's AB. Now, what's the critical point of F? Yes, sir. So usually everything I do in class is you need to know. I mean, sometimes I say you don't need to know this. For example, if you have a motivation or something like that, I say you don't need to know this. But all the proofs usually, everything that I write in class is fair game. Okay? Fair game. Great. Suppose F, so what did we call a critical point in Calc 1? It's a point where derivative is 0 or the derivative does not exist. Same thing, we say AB in the domain of F belonging. The domain of F is a critical point. If or how do we say? Or if gradient of F gradient of AB does not exist. Basically, at least Fx or Fy do not exist at AB. Okay, so I'll skip the proofs. So if F is differentiable, if F has a local max or local min at AB, similarly as to calculus 1, AB is a critical point. Now, you know, in this course, I think we will not have to worry about non-differentiable functions. Functions that are not differentiable. Okay? So everything we'll have usually will be just solving derivative is equal to 0. And then we'll be fine. Okay? Great. Let's do a small example. Or, yeah. Okay. Now you found critical points. You found the critical points. In calculus 1, you found the critical values. What did you use them? You classified them, right? Local max, local min. We remember? We remember? Yeah? What did we do to classify the critical points? If F is differentiable. F is differentiable. What did we do? Yes?
Did you find whether the derivative is negative or positive on either side?
Very good. That's one way. What's another way? Yes? Yes?
The second derivative.
The second derivative test, right? Remember the second derivative test for calculus 1? Yeah? Now we'll have a second derivative test in calculus 3. Okay? I will just write it down. I will not prove it, because you don't need to know the proof. You just need to know the result and how to apply it. Is that fine by everybody? Yeah? Okay, so I'll do that here. Okay, now how to classify FAB? Like, is it a local max or a local min? The answer is the second derivative test. Okay, of course, this assumes that f is twice differentiable and the partial are continuous. Okay, the second partial are continuous. Okay, suppose that okay, so now we will not worry about non-differentiable. Okay, everything will be differentiable. So we'll forget points where f does not exist. Okay, so suppose f xy is a differential function. Is that 2 times is twice differentiable, and that fxx, fyy, fxy, fyx are continuous. Suppose that is equal to 0, 0. So I have a point AB where the gradient is 0. Then okay, so here you can also relax that. Can we relax to continuous, I think, at AB? At AB. Okay, suppose. Anyway, continuous at AB. All the examples will do will be continuous everywhere in the domain, so we will not have to worry about like strange things happening. Okay? But anyways. Now, very, very long. Let B this is a matrix. This is a determinant of a 2 by 2 matrix. We call it the Hessian. Hessian. We don't need to know it. Don't worry about it. But this plays the role of the second derivative in 2D. Okay? When you say the second derivative of f, you mean all possible second derivatives. X twice, y twice, xy, and then yx. Okay? What is the determinant? Can you help me? How do you find the determinant? Right? We agree? Because fxy and fyx are continuous at AB by Clairaut's or near AB. By Clairaut's theorem, they're equal, right? So this is my determinant. Now this determinant will tell you almost everything. Okay, let's get ready. This stuff you'll have to know by heart. Okay, you'll have to know this. I mean, there are other ways of checking it, but this is the way that you should know. If 1 D is positive and fx AB is positive, F, AB is a local. Two. If B is positive and is a local max. If B is negative, then FAB is neither a local max or what did you call this in what did you call the point in calculus 1 where you could not neither a local max nor a local min? Saddle? You call it saddle? What did you call saddle?
Inflection point.
Okay. But what did you call a name for something neither a local max nor a local min? Okay. Because the book says it's a saddle point. Okay, the book says they call it saddle point. Okay, I mean I've seen this before. So yeah, in case C is not a local max or a minimum, and AB is called the saddle point. Inflection point, well, what is an inflection point? It's where the second derivative vanishes, right? And it changes sign, right? Does that have to do with the local max per min? I don't think so. Yeah. Anyway, on 4, if D is 0, I don't know if they say it. If D is 0, they say, oh yeah. They said, yes. No information. Still have 25 minutes. We could do two examples and apply this. Okay? So I will keep this here so that you guys know what's happening. And then I'll have to erase here. Is that fine? So that we can see what's happening. Let's see my notebook. I have examples. Definitely I do. Find local maximum of xy. Okay. Fine. The local max. Okay, now fxy, what is that equal to?
X4 plus Y4.
Minus 4xy plus 1. So, before I find anything, is my function differentiable? And are all the derivatives continuous and whatsoever? Everything nice I have. Okay, great, so I have to worry about nothing. So all I have to do to find the critical values is to solve the gradient is equal to 0, right? How did you do in class 1? You solve the derivative is equal to 0. The same thing here now. What is my gradient? I take fx, xy. What's the derivative of fx? What's the derivative of f with respect to x? It's 4x cubed minus 4y, right? Yeah? is fy? It's 4y cubed minus 4x, is that right? Yeah, very good. Now you need to solve these two equals 0. What do you get? You get x cubed is equal to y. Agreed? 4x cubed is equal to 4y. Divide by 4, you get x cubed is equal to y. So far so good? Yeah? And then 4y cubed is equal to 4x, so you get y cubed is equal to x. How do you solve this equation? So x cubed is equal to y. So what is y cubed? This implies that y cubed is equal to what? X to the so y cubed is x cubed cubed. X to the, you see that? Yeah? Try. 2 cubed cubed. What is 2 cubed cubed? It's 8 cubed. Oh man, 8 cubed, what is that? It's 8 times 8, 64. 64 times 8, so it's 640 minus 128, so it's 512, right? Yeah? Yes? Now what's 2 to the 9? 2 times 2 is 4. Times 2, 8. 2 to the 4, 16. 32. 64. 128. 256. 512. Right? This how we check it. This. If I forget anything, I plug in number. And then we check. Okay? So, x cubed is y, and x9 is equal to x. Now, you want to factor x9 minus x. So it's x times what? Times x to the 8 minus 1. This is x times x to the 8 minus 1 is equal to 0. How do you factor x to the 8 minus 1? Is x4 minus 1 times x4 plus 1, right? Right? What are the solutions here? You have x equals 0, or x equals 1, or x is equal to minus 1. Agree? Everybody? Solve this one here. Solve this thing here. Yes or no? Yeah? Okay, now if x is equal to 0, what is the value of y? 0. If x is equal to 0, this implies that y is equal to 0. If x is equal to 1, what is the value of y? Implies y is equal to 1. And this implies y is equal to minus 1. So what are my critical numbers, critical points? It's where the gradient is 0. Okay guys, are we good here? What happened? What happened? We're good? Just like that? Yeah. Are we good? Yes, sir.
Can you get the focus of this equation?
Pardon?
Like the tag one, you have x and then
Here?
before the next one.
Here?
Yeah, like when you get that to 0 and the x 1 to the left.
So you get x4 is equal to minus 1.
Yeah, can you get the focus?
Yeah, you have a complex number, an imaginary number, I. But this is always positive in the reals. Right? Have you guys seen complex numbers? Yes. So if you take I, you get a solution for this one. But in the real numbers, if x is a real number, x4 plus 1 is always positive, strictly positive, so it will never be 0. Here? Oh, because take minus 1 to the 4, what do you get? Okay? So you have x4 minus 1. What is that? Factor that again. X squared minus 1 times x squared plus 1. Right? Calculate again, this is x minus 1, times x plus 1, times x squared plus 1. This here, this has no solution, because it's always, okay, is that good? Great. We are all good with factoring stuff, yeah? I hope so at least. Great. Anyways. Now, can I erase this or not? Can I, yes sir?
Is that the same for f, y, y?
Ah,
That's one.
so it has to do with positive definition. Did you see this in linear algebra?
Positive one?
Definiteness?
No.
Okay. I don't think so. No, it's not the same thing. It's not the same thing. Because if you have a leading term, I don't think it's the same thing. Because it has to do with positive definition. Yeah.
You said we're not going to consider it, but if the derivative doesn't exist, then it's not local maximum.
Not necessarily, but you should consider these points as candidates for local maximum.
Okay, like y is square root x. At point at 0, the derivative doesn't exist. Right?
Yeah.
That's not local maximum.
It's not a local max or local min, but it's an absolute max. Okay. So, but you should consider this in your studies. Like when you study that, you should consider when you study the derivatives, consider these as critical numbers. The points in the domain where f is not differentiable. Right? Did you do this in class 1? So if you took y equal root x on 0 to infinity. Now, well, that's not a good example because really you cannot talk about differentiability of root x at 0. You can talk about left or right differentiability, like because differentiability is always on an open interval. Okay, so but I mean again, we'll not have to worry about that. Okay, we will not have to worry about that in this case. Anyway, so my critical numbers are here. Now the way I prefer to do it is this one. You plug in your point AB. And you compute D, and then you classify. So what is your point AB? 0, 0. Let's compute the second derivative. What is fx xy? This is 12x, right? This is 12y. So what do you have? You have 12x, 12y. What is fxy? This is minus 4, right? And what is fyx? It's also minus 4. This is dxy. Which, I mean, I didn't define for all this y, but I just defined for AB, but that's fine. Now, what is fxx at 0, 0? What is fxx at 0, 0? 0. What is d at 0, 0? Wait. Did I make a mistake? No, that's fine. What is d at 0, 0? Everybody? Plug in 0, 0. What do you get? It's 4, 0. 0 minus 4, which is minus 16. So it's minus 16, which is negative. What can you say here? Side effect. Now let's look at 1, 1. What's fx of 1, 1? It's 12 times 12. So d11 is 144 minus 16, which is 128, which is positive. And fxx at 1, 1 is 12, which is also positive. So what you have here, you have a local min at AB. At 1, 1. Now let's take minus 1 minus 1. It's going to be the same thing. 12 No, I think it should be the same. Yeah, it should be the same. What is fxx? 12x. So 12x is minus 1.
12x squared.
Good. Thank you very much. You see, this is a very big mistake. Very big mistake. Very big mistake. Yeah. Luckily, it doesn't change the answer. It's 1 and minus 1. And how did I know that I made a mistake? How did I spot it immediately that I made a mistake? How can you spot immediately that there's something wrong? Flip x and y on the function. And flip minus x and minus y. So if you flip x and y, you can flip them. You have a symmetry, right? Between x and y. Change x to minus x and y to minus y. Okay? So thank you for the person who corrected this. So I get 12, which is strictly positive, and the determinant is still 128. Positive. So what do I have here? Minus 1, minus 1. Okay? Should you do more or not? Do you want to do more of this? How much on yes, sir? Okay.
How did you recognize this mistake? I don't get it.
Look at the symmetry. Just think of it on the symmetry
Okay.
of the function. You have a symmetry in x and y, and a symmetry in minus x and minus y.
What's my even?
Something like 12. What is even? Yeah, this. So you take f of, but you have also a symmetry between x and y. Okay, great. Should we do one more? Yes. Where? Local min at 1, 1. Local min at minus 1, minus 2. Should we do one more? Let's see. We pick a harder one. No, let's pick an easier one. Big fxy is y e to the x minus 1. So what is fx, everybody? It is just y dx. And what is fy? Is dx minus 1. What is the only solution to this? If I need to solve these two equal to 0. This equation tells you that y must be 0, right? Because e to the x is never 0. And this equation tells you that e to the x must be 1. It means x is 0, right? So x is 0. So xy 0 is 0. Only critical point. Let's look at my second derivative. What is fx xy? You differentiate with respect to x, you get still y dx. Differentiate with respect to y twice, what do you get? 0, right? Differentiate with respect to what? What to y and x is ex. Okay? Now look at this. Look at d 0, 0. What is d 0, 0? It's fx 0, 0, fy 0, 0, minus fy 0, 0, 0 minus 1 square root, right? So it's minus 1 negative. What is that? 0, 0 is a, you have a standard point. Okay, we do one more?
Yes.
How much time we have left?
8.
No, I'm just asking, you know. No, I want to stay, you know. But I mean, it's tiring. 2 hours and a half is not. You can see from the way I speak. 2 hours and a half is a bit tiring. Pardon me? Change it to what? It's. I mean, we could do that if they let the course go to 2 months, right? Yeah.
Someone.
Yeah, I don't want to new thing either. Let's see. So let's pick. Okay. So again, now I'll try an example from the book. I'll try an example from the book, and then we'll see how it goes. Okay. So fxy, I'll write here. fxy is x minus y one minus xy. Okay, let's differentiate. Everybody, let's try to differentiate with respect to x. We know to differentiate or not? Yeah? Differentiate with respect to x. fxxy. So it's minus, well, I mean, you could expand that. Let's try to expand that. It's not a bad idea to expand that. X minus x squared y minus y plus xy squared. So, yeah. Is that right? Is that right? X minus x squared y minus y minus plus xy squared. Yeah. Differentiate with respect to x. What do you get? You get 1 minus 2xy. Oh man, that's going to look bad. Plus y squared. Is that right or not? Is that correct? Okay, let's differentiate with respect to y. That looks bad. So what do you get? You get minus x squared minus 1 plus 2xy equals 0 equals 0. Let's see. Let's see. So let's see what we get here. We get y squared minus 2xy. You see that or not? Plus 1 is equal to 0. And then you get x squared minus 2xy. No, there's nothing to be here. Plus 1 is equal to 0. Among the only examples I picked up bad one. But let's make sure my derivatives are correct. Are my derivatives correct? Okay. Great. So how to solve this?
Can't you subtract the 2 equations?
Yeah, exactly. That's the only thing. But then you get y squared is equal to x squared, and then you get y is equal to plus or minus x, right? And then you have to. This is the only way to do it. You subtract the only thing. One way you can do it is that you can add a y square on both sides, and then set them equal. But anyways, no. Let's subtract the 2. So if you subtract the 2, let's call this 1, and let's call this 2. 1 minus 2, what do you get? You get y squared. Oh, wait a minute. Let's write it this way. Agreed? Those two are equal to this one.
Yes.
So this implies that y squared is equal to x squared, and y squared is equal to 2xy plus 1. So this implies y is equal to x y is equal to minus x. So if y is equal to x, what do you get? You get, so if y is equal to x, okay, I'll erase here. Can I erase here now? Okay. If y is equal to x, if y is equal to x, what do you get? You get, if y is equal to x, you get x squared is 2x squared plus 1. Does this have any solution? No solution, right? No solution. This is the same thing as x squared is equal to minus 1. And if y is equal to minus x, what is y equal to minus x? So it's x squared minus 2x squared, right? Plus 1. Okay, let's make sure I didn't mess it up. So you get like 3x squared is equal to 1. So you get x is 1 over root 3. Is that right? Is that, yeah?
Is this supposed to be y squared is equal to 2x minus 1 or?
Oh man, oh man, oh man, oh man, oh man. This is good. This is good. You see, like it's now that's a good. Now that's good. So x squared is equal to 1. So x is 1 or minus 1. Now here you get. Well, here you get 3x squared is equal to minus 1. So no solution. Thank you very much. So if x is equal to 1, what is the value of 1? Here y is equal to x. And if x is equal to minus 1, minus 1. Okay? Finish this at home. See you Tuesday.